All right, I'm gonna start. No one is here again, but that won't stop me from doing some U-sub problems. Okay, U-sub. I'm just gonna dedicate this entire session to just doing these because I know they're difficult, and I know that y'all could probably use some more practice. And if I just sort of show you my thoughts about how to go through one, that might help y'all a little bit. So we're just gonna do like try to get through as many examples as possible. I have 7. This is a 1, by the way. Sorry. Okay, integral. This is a general integral from 1 of 1. This is the general integral, so indefinite integral from of x times 1 plus x squared all to the 9th in the dx. All right, so theoretically, we could do this by just like simplifying this, right? This would like be out like 9 times, and then you like multiply, and it would just get really, really messy and gross. I don't want to do that. That is too much work for me. It should be too much work for you guys as well. You have to distribute your x, and then you could do it, but it's going to be gross. It's going to be ugly. You don't want to do that. There are better ways. The best way to do it is by using U-sub and by recognizing that this 1 plus x squared is basically a function within x to the 9th function, right? So if we have this like, okay, g of x equals x to the 9, f of x equals 1 plus x squared, then right here is this g of f of x, right? Where it's got your, you got this, right? That makes sense? Or like g of 1 plus x squared. And so anywhere you see an x in g, you plug in a 1 plus x squared. That makes sense? Yeah. And then this x out here basically just to help with us do the U-sub. If that x wasn't there, we wouldn't be able to do it. But that's sort of like not your problem. So the first thing to sort of like think about when you encounter an integral like this, or just any integral, is like, okay, can I do something easy? If it's just your regular old trigonometric ones, you can basically be like, okay, maybe I can just sort of like do from like sine to like cosine to sine, something easy like that. You can also like vibe out the power rule ones, things like that. But most of the time, if you run into something that you're like can't do pretty quickly, or without doing some fun like arithmetic to move around the variables, you're going to have to use U-sub. So always be on the lookout for U-sub. When you look at for U-sub, you're looking for like an inside and outside function similar to chain rule, because U-sub is basically chain rule but reversed. So in this case, this inside function is sort of what we're going to be looking at, whereas this outside function is sort of not something we want to deal with, because we could make just like x u, but I think Bradshaw went over something in class where like you never want to make x u, because then you basically just like replace all the x's with u's and it's like basically worthless. You always want to make x u something interesting, right? So you could also make like u 1 plus x squared to the 9th, but then again, like that derivative is also going to be really ugly. You know, you're going to bring this 9 down, make this an 8, then have to do this whole chain rule thing. That's kind of gross. Usually your u is going to be something simpler. So in this case, we're going to be using u was 1 plus x squared. So the steps for U-sub follow the exact same pattern literally every single time you do it, okay? You find your u, you derive with respect to x. So 1 becomes 0, it's 2x, dx, yeah. And then you look for a way to plug in something that you've created here into what's up here. But you want to get rid of as many like x's as possible and substitute in the u. So you're looking to plug to like get rid of this dx and get this du in here, then as well as like any other outside x's and make those just basically go away, right? So right now we have this 2x dx equals du thing. So we could do a direct substitution if there's a 2 here, right? If there's a 2 right here, but we don't have a 2 there. So we can't really do that instantly. But we can take this 2 to the other side, and then that's just x dx over here, and then substitute it, right? So that's fine. Awesome. And now we can do this cool little like substitution, which is this is where the U substitution part comes in, right? So this x goes away, this dx goes away because you basically replace it with this 1/2 du, and this substitutes in for here. This u goes in for 1 plus x squared, and we're left with just this 9, right? So I can rewrite this. X dx becomes just 1/2 du. Cool. So I'll write just like 1/2 here, du later, du. I'm just gonna write it closer to here. And then this whole 1 plus x squared thing, we can just plug in a u for it. We don't really need to worry about it. Yeah. We can just basically plug in a u for it. The 9 stays there. So it's basically just a pretty simple substitution in this case. From here, we can make it look a little nicer. You know, this is a constant and an integral. If a constant's ever multiplying it by anything, you can just take it out. So I'm just going to do this. Sorry, that's an awful Riemann sum thing. And then just do u to the 9th du. Cool. Now this definitely looks manageable because now we can integrate this whole thing with respect to u. And luckily our variables that the only variables that we have left over are u. So that kind of like works out well for us, I think. So how do we integrate this? Well, you add 1 to 9. Okay, so we have u10, and then you need to divide by that new exponent. So then you get 1/10. And multiply that by 1/2 because it's from up here. And plus c. Yeah, so I know that's kind of like a couple of steps there. But again, you just add 1 to the exponent. You multiply by the reciprocal of whatever you just added, and then also make sure to include any constants that you have outside of your integral. I'm going to simplify this a little bit, make it 1/20th, or probably just like u to the 10th over 20 plus c. And then, because we want an answer in x, we just need to plug stuff back in. Cool, and that's our answer. So this indefinite integral got us to a family of functions, right? This family of functions differs, each function in this, because like c is some constant, that's like a real number, right? It differs basically just by like a number that sort of is going up or down, right? So I don't know what this looks like, but if it was like this, it could also look like this, it could look like this, or something like that. So it's just all about like where it is in the y stuff, sort of. That makes sense. It's just moving up or down. And there's like infinitely many of those. So it's like a family of functions. Yeah, cool. So that's like a good example of U-sub. Now I want to do it with a definite integral. And funnily enough, it's going to be the exact same function that we're going to be integrating. So don't worry, guys. Don't be too hard. This is 1 plus x squared, sorry. Even though it really doesn't matter. All right. So there's a couple of different ways that we can go about doing this, sort of. We can basically just like do everything how we normally did it. You know, do the U-sub, plug back in, do the U-sub, find the derivative with this, the integral with respect to u, plug back into x, and then solve for 1 and 0, right? So I can sort of like run you through how I would do that. So u equals 1 plus x squared here. Take the derivative, it's 2x dx, and then that goes to 1/2 du equals x dx. So this is going to simplify or substitute in as 1/2 u to the 9th du, right? So this is also just 1/2 0 u to the 9th du. Cool. This du is very important. Otherwise, you couldn't really integrate it at all. Cool. And then, you know, just the integration, pretty simple. So I guess we found out it was 1/20th u to the 10th from above. And I don't need to add this plus c, right? Because it's a definite integral. So I'm going to do that like evaluated for 1 and 0. So basically just like move it to the other side. And this notation basically means, well, this is like x, right? Because we started out in x here. How does he like this? Well, actually, I'm not going to write this yet. And then this substitutes in for 1/20th x squared plus 1 to the 10th, right? And now we have this, it equals this. How's it going?
How's it going? Oh, there it is.
Oh, yeah. Sorry, you had some stuff. Yeah, don't worry about it. You're good.
Appreciate it.
Of course. So now that we have it sort of like in x, we can basically just like sort of actually evaluate for this, right? Because these bounds that we were originally started with were defined for when we had our function in terms of x, not in u. So we can't use it for u. So to simplify this, we plug the 1 in, we kind of take the 1 down over here, and then subtract, and then do a minus sign, and then plug the 0 in, right? So how we're going to do that is we're going to do like a 1/20th, plug a 1 squared plus 1 to the 10th. Yeah, so that's like the left side. Minus, and then plug 0 in. So 1/20th, 0 squared plus 1 to the 10th. Simplifying this, we get 2 to the 10th over 20, which is, some number. I'm like pretty sure that's what it is. And then you subtract it by just 1/20th, I believe. Cool. 2 to the 10th, what is that? I should know what that is. I think it's like 10/24. Let me like do it really quick. Yeah, it is 10/24. Sick. Okay. So yeah, and then that would be our answer. And notice that this is like an actual value, right? Whereas our indefinite integral got us this family of functions thing. So two very different things that the same like idea of integration will get to us too, right? So definite integrals, you're dealing with values. You get an actual value. So this like equals some number c. I actually have it written out here. It's 51.15. Whereas our indefinite integrals get us a family of functions. So there's a difference there. And that's because definite integrals basically represent that area under a curve, right? So you have like this, and say this is A, this is B. The integral of that, the definite integral from A to B of this is this area. So this represents the area from 0 to 1 under the curve of whatever function this is. Yeah, cool. All right, so that was like one method of solving this definite integral with U-sub. The other method, though, might be a little bit better and doesn't force you to resubstitute your x, your whatever you choose to like your x sort of function to be for u. Doesn't force you to sub that back in, right? So it basically involves changing the limits of integration with respect to changing it in terms of u and rather than in terms of x. So I sort of write this out again. So 1u x 1 plus x squared 9 dx. I can do my normal u sub, right? So I get this integral of 1/2 u to the 9th du. Yeah. But if I want to if I want to avoid needing to resubstitute in, such as what I did for this step right here, when I plugged in 1 plus x squared for u, I can change my limits of integration based upon what we set u to be equal to in terms of x, right? So if I know that this 1 equals x, this equals x, then I want something that equals for u instead, right? So I know that if u equals 1 plus x squared, I can plug in 1 and 0 here, and then get something for like the u values or the u variables instead, because that's what we're going to be integrating and dealing with, right? So if I plug in 1 here, u equals 1 plus 1 squared, u equals 2. Then u equals 1 plus 0 squared, u equals 1. So that means that wherever I had x for 1, I want to put 2 for u. And wherever I had 0 for x, I want to put 1 for u. Cool. And now we can basically just integrate without needing to re-substitute in our 1 plus x squared, right? So this goes to 1/20th u to the 10th to 1. And I'm pretty sure that if you solve this one, so what is it? It is u to the 10th over 20 minus 1 to the 10th, or just 1 over 20. You'll notice that that's the exact same thing we got here, right? So it also equals that 51.15. Cool. So these are all pretty simple examples, but these are basically the only ways that you're going to be dealing with more complicated integrate U-substitutions, and like the types of U-substitution that you're going to be dealing with. Either there's going to be indefinite, you can do the method where you go from x to u and then back to x, or the method I prefer is where you start with x, you u-sub, and then you change the bounds of integration based upon your definition of u in terms of x, and basically plug your original bounds in to get something different in u, and then you like sort of like figure everything out from there, if that makes sense. Hopefully it does. I'm going to continue on to some more complicated, possibly complicated examples now. Cool. So 3. Integral cosine pi theta. Now, remember that when I write it out with theta as being the variable, this variable could literally be anything, honestly. It could be like a smiley face. It could be like, I don't know, a color. It doesn't really matter. Our naming of x is sort of arbitrary. So when we sort of deal with things like theta or deal with things like u, it's all relative to what the rest of the function is defined as. So we know that pi is not something that we're sort of dealing with. We're dealing with theta instead. You could change this to be like d pi, and then honestly it would be pretty similar, except you'd basically have your pi be your variable instead, and then I treat theta as a what's the word, as a constant, but that's sort of besides the point. So when we look at this, we first can recognize that there's something on the inside of this cosine function, right? Because if there wasn't this little pi, all we would have to really do is just say, oh, boom, sine of theta, right? Sine of theta, right? Because cosine theta d theta equals sine theta, and the derivative of sine theta equals cosine theta, right? So that's pretty easy. But we have this little pi here. And so normally as you get better at doing integrals and stuff like that, you can probably just like eyeball this one, but it's always safe to use u-sub. And so whenever you have this thing where, again, you have this function on the inside, so our inner function right here is like f of theta equals pi theta. So pi is just any constant. And then our outside function is that g of, is that cosine theta, right? So we're dealing with another inside-outside function thing again. So normally you want to sign u to be whatever the inside function is. So I'm going to do u equals, that's an awful u, pi theta, derive, so du equals, well, we're taking the derivative with respect to theta in this case, right? So this is basically x. It's a variable. So since this is a constant times a variable to the power of 1, we just get rid of it. So we just left with pi and d theta. So now we have this d theta thing here, right? Okay, well, we can substitute that in, but we have this pi, so we need to move it over. Now we can substitute, because now we have a d theta that can basically just directly be used as a substitution with 1 over pi and du. So now we have this integral 1 pi cosine. I'm going to plug my u in, because that's what I chose for my u, and my du. Cool. Now I'm going to take my 1 over pi out, because it's just a constant after all. Sine of u. Sick. Good thing we found out how this works up here, right? Because now all we have to do is just derive with respect to u, and it's a pretty easy derivative. We have to integrate with respect to u, and it's a pretty easy integral to do, right? Cosine of u, the integral of that, or the antiderivative of that is just sine u. So you have 1 over pi times sine u, right? Plus c, I guess. But now I need to plug back in again for theta, for my to get rid of my u, because we want an answer in terms of theta and not in terms of u. So final answer will be 1 over pi times sine pi theta plus c. Cool. And you can check this is right by using chain rule, right? So if I was doing the derivative of 1 over pi sine pi theta, yes, plus c. C would go away. Sine would become cosine pi theta, right? And then I have this right here, because it's just a constant out in front. But then I need to activate chain rule, right? I need to remember chain rule. So I'd multiply by the inside function, by the derivative of the inside function as well, right? And we decided that that inside function was pi over theta, or pi theta, right? So the derivative of pi theta, so derivative of is just pi, right? So I multiply by pi, which just equals pi's cancel, cosine pi theta. That's it. Pretty cake. Yeah. Awesome. Okay, next example. Gonna do another definite integral. Whoa. Gonna do with 1 equals x. And honestly, if you need help remembering, which values are for what terms, are for which variables for the bounds of integration, you're more than welcome to do like the 1 equals x, 0 equals x stuff, just because it can get confusing. And in future math classes, in Calc 3, for example, I did that all the time just because I would sort of get my bounds confused, when the bounds are actually going to be the more difficult part of finding how to do these different integrals, just because they'll sometimes include variables themselves. So it's like a whole another thing. So sort of never be afraid to just write out 1 equals x, 0 equals x, and then in the future, like 3 equals u, 5 equals u, something like that. Okay, so the actual thing we're going to be doing is this. This is the function that we're trying to integrate. Cool. So the first thing I want to realize is be like, okay, inside function, outside function question mark. That's what that looks like, right? You have an e to the x and also a negative 2x. So doing my little u sub thing. Negative 2x is my inside function. Deriving negative 2 dx. And gonna bump that over to the side again. So negative 1/2, my bad. Du equals dx. Cool. And now I'm ready to substitute super easily. Yeah, e to the u. So I guess I have to remember the negative 1/2. E to the u du, right? Because here's a negative 1/2 du part. I'll just like highlight it. And then this goes right here, right? But I need to worry about my bounds of integration. So we're going to take whatever our x values are and then basically convert them into u. U equals -2 times 1 equals -2. U equals -2. 0 equals 0. So now I can just plug that in. Now, if I really wanted to, I can split these bounds of integration just because right now, this is less than, the top one is less than the bottom one. And typically we don't like that. We like the top one to be higher. So what I'm going to do is flip the bounds of integration. And what that does is it costs me a minus sign. So I have to multiply this whole thing by -1, but that kind of works out because I already have a -1/2. So I'm going to simplify this to being 1/2. Let's bring it out in front. 0, -2, e to u, du. And now this is pretty easy actually. So you mean the derivative of e to the x is just e to the x, right? Therefore, the integral of e to the x is just e to the x, or the antiderivative is just e to the x. Same thing with e to the u, I guess. So if we just do a 1/2 around all of this, we know that e to the u sort of is our antiderivative. We just need to solve it for u -2. Remember, these are u values. We already plugged in for, sorry, someone's like calling me. Just a second. I'm sorry. Okay, sorry, that was kind of unprofessional, but we're back. So remember, this is a u value, because of how we like plugged in right here. Yeah. And so we're carrying that over. So now we just need to like plug our different u values in and get something. So what'll this look like? We'll have 1/2 around the whole thing, because 1/2 goes around like all of this, right? So plug 0 in for u, it's e to the 0 minus e to the -2. Yeah. Equals 1/2. E to the 0 is just 1 minus 1 over e squared, right? Because e to the -2 is basically the negative exponent means it's like, in the denominator, sort of, if that makes sense. And then that simplifies to 1/2 minus 1 over 2e squared. Cool. So, hopefully you sort of understood the path I took to get through this problem. All right, just a few more. I thought I'd like this stool, but it's really just like not doing it for me. I need something better to sit on or stand on. Okay. Okay, I like this problem. Cool. Let's do this. X to the 5th square root of 1 plus x cubed dx. All right. So first thing you see when you notice when you see this function, or the first thing you should think about, is there an inside function that sort of looks like it's on the inside of another outside function? Well, 1 plus x cubed is under square root. Square root is like a root x function, right? So you got your place like this. Then we also got 1 plus x cubed, so g of x, f of x. And there's no correlation to like inside outside function. I'm just like doing this randomly for like f of x and g of x. So this could go inside that. Okay, that looks good. Maybe we can try using that as u sub, as our u substitution, right? Because if we were to do the whole square root thing, then the derivative would get really messy after we try to do the whole substitution, and it's like it's because the 1/2 comes down and then chain rule. Oh, it's just kind of gross. And then the x to the 5th, I mean, you can sort of see that, okay, this 5 will go down. It'll be 4x to the 5x to the 4th, but we're working with x cubed, and then where's like our +1, stuff like that. It's always good to sort of use U-sub with these constants as well, because it normally goes to 0. And then once you have just something in like x form, or then it's really easy to substitute stuff in for that, right? Yeah. So we're going to choose u to be 1 plus x cubed because of how it's like our inside function. We're going to derive both sides. 1 goes away, 3x squared, sick, dx. Cool. Now something you might notice, okay, well, we have this x squared, but we're looking to get rid of this x5th, because we don't need to worry about what's inside the square root, right? Because the u, we can deal with that. We can just plug the u in. But this x5th, we're kind of missing something here. We can get to that in a second. Let's sort of move this 1/3 over just for fun. Or just 3 over, I guess. Square dx. Okay. Now I can rewrite this. Okay, well, we have an x squared, so we might as well try, right? So we got this x cubed. Okay. Well, sorry. If we split this x to the 5th into like x cubed and x squared, we know we can plug in for the x squared. So that's why we have like this x cubed left over times, what is this, 1/3 du, which is sort of over here. And then also don't forget our root u thing, right? So, okay. So we're like halfway there, right? We plugged u in for our 1 plus x cubed. We plugged in our x squared dx for part of what we have in the original thing, but it's not sort of everything that we're trying to look for, right? Because we still have this x cubed to sort of get rid of, and I'm not really sure to do that. Oh wait, hold on. We have this u equals 1 plus x cubed thing. What if we I don't know, wrote x cubed to be equal to something in terms of u instead of the other way around? Because I mean, this still sort of holds, right? We defined u to be something. So what if we took the 1 over u minus 1, right? Equals x cubed. Okay, well, what if I just plugged in u minus 1 for x cubed? That could work, right? Now that looks nice, doesn't it? We're getting there. we have everything in terms of u now, which is great. And now we really need to do is sort of simplify. Maybe we can distribute this u in, pull this 1/3 out of the integrand. I think that's what this is called. Make it sort of multiply by everything because it's a constant. See where that goes. So we got this 1/3 integral. Distribute this u. So what would this be? U to the 3/2, right? Because, excuse me, this is a 1. So 1/2 plus 1. That's how multiplying exponents work. That would be 3/2 minus u to 1/2 du. Now this looks something that we can integrate for sure. All right, let's try to do it. Okay, we got a 3/2, so you got to add 1. That's u to 5/2, multiplied by the reciprocal 2/5. Nice. And you can see that if you do the derivative of this, 5/2. Okay, that goes that 5. If you multiply the 5, this whole thing by the 5/2 before you subtract 1 from it, the 5s cancel out, 2s cancel out, so then you're just left with 1 here, which is what we're looking for, and this just goes to 3/2, which is also what we're looking for. Okay. Add 1 to 1/2. Okay, that's 3/2. So you got u 3/2 multiply by the reciprocal, say 2/3. And then plus c, but we don't really need to add that right now. Well, I guess we can just plus c it at the very end. The reason if I put it inside the parentheses and I distribute the 1/3 to the plus c, and that doesn't really mean anything because c is arbitrary. So I'll just add the c at the very end. As long as you have the c at the very, very end by itself, you'll be good on any problem. Just make sure that you include it somewhere. Yeah. Okay. So I'm actually just going to leave it in terms of this, just because simplifying it would kind of be annoying and gross. Your teachers shouldn't really care. Your professors shouldn't really care. Your TAs shouldn't really care. So this is totally fine. However, we need to plug in back in to get this in terms of x, right? We don't like u. So we got our 1/3, 2/5, 1 plus x cubed, 5/2, cool, minus 2/3, 1 plus x cubed for our u, 3/2. Then we plus c. Can't forget that. All right, and that is what our answer is looking like. So yeah, pretty cool. That's what we got. I'm pretty sure I'm just like double checking to make sure that I did it right. Yep, everything looks good. So yeah, that's how you sort of complete something more similar to complicated. So I guess that sort of adds a layer of how to solve one of these. If you do your U-sub and it seems like you're doing everything correctly, but you're still left with something else that's an x in your integrand, maybe try looking back at what you originally used as your U-substitution and try mixing that around to see if you can, do another substitution like this where you set, again, in this case, it was x squared as something in terms of u, and then plug that in for it. And then you can sort of like work with it. So just be on the lookout for that. That might come up. Okay. 2 more problems left. Okay. I like this one. Three x squared plus 6 over x cubed plus 6x plus 2 dx. Interesting. So we don't really have a we don't really have like an easy what's the word, inside outside function to really like view from this one, do we? It's kind of hard to tell what we're going to do with this. Maybe you can try to like look at the differences in how the relationship between like the numerator and denominator. One thing I have noticed is that this is actually the derivative of that. Well, I mean, I know that in U-sub, we do take, something to be equal to u and then derive that. So maybe we can use that to our advantage. So I know I can rewrite this, right? To be 1 over this x cubed 6x. Hopefully to let you guys see it better, times 3x squared plus 6 dx, right? Okay. Well, maybe if I take this to be u, I derive it, and then I have something I can substitute my du in for. Yeah, that'll work. Okay, so let's do u equals x cubed, 6x plus 2. Derive 3x squared, bring the 3 down, minus 1, plus 6, get rid of that variable, and the 2 goes away. And of course, dx. I mean, yeah, this is just pretty as clear cut as it can be. You just sort of substitute in 3x squared plus 6 dx in for du, and then take your u and then plug it in for the denominator here. So, I mean, they've sort of done us a little nicely here. So it was a big 1 over u and a du. And so all this messiness just simplified so easily just because we chose a correct u value or a smart u value, right? Or a smart u substitution. So now we just have to derive this, right? Well, that is just ln of u, the absolute value of u, right? Plus c, of course. And then we just have to substitute back in. So we need to take our u in terms of x and substitute back in the x parts. Absolute value is q plus x plus 2 plus c. And that's how you do that one. So look out for these interesting U-subs when you're dealing with these fraction ones. If they give you an integral, there's going to be a way to solve it using U-sub. So really just make sure you're looking out for sort of, okay, I have this one part of a function. I take the derivative of it. Can I plug it in for somewhere else, for another part of it? So right here, we take the inside of this, we take the derivative of it, and we could use that to plug in for somewhere. So like right there, right there. Same thing for what we've, where should I say? We did in our first example, right? We did this part, we took the derivative of it to get x dx. Luckily, there's an x right there, so you can just plug in. So that's also something to look out for, in addition to like the inside-outside function thing that I mentioned. Okay. So one final example before I end the session. Definite integral from 0 to 1, square root of 4 minus 3x dx. So they don't really give you a clear example of how to choose a U substitution than this. You know, there's really only one option. There's the 4 minus 3x, that's the inside function, and then your root x is your outside. I'm not sure what else you can really use for you to like get you anywhere. So yeah, that's like pretty clear and cut. Okay, so let's just kind of like go through it. U equals 4 minus 3x. Derive, as always. 4 goes away, minus 3 stays. Add that dx. My bad. Add that dx on the right side. So you're doing with x, you add the dx. U, you add the du. So this x does not go to like the dx. You sort of add the dx because you're deriving with respect to x over here, right? And then this x goes away because of how it's just by itself. Cool. And then, well, we don't really have a -3 here, but because we just have a dx, so we're going to move it to the other side. -1/3 du equals dx. Cool. All right, now we can sort of like plug stuff in. But before we do that, maybe we should deal with our bounds, right? Our bounds, just because we sort of want to fix those. So we know this is x, right? This is x. So we can just do u equals 4 minus 3, 1 equals 4 minus 3 equals 1. Cool. U equals 4 minus 3, 0 equals 4. Well, just equals 4, right? Cool. So now we have these cool u values that we can use. So do 1, 4. We got this -1/3, right? And then we got this u that we can plug in for here. So it's just square root u, and then our du as well. So to highlight everywhere I got stuff from, did this from here. I got this from here. And I got this from here. Cool. Now, again, I'm going to flip these just because it's like 4 to 1, and I like it when it's like 1 to 4. Luckily, we do, again, have a minus sign, so I can do that. If I didn't have a minus sign, it'd be fine. It's just working out that way, so I, can just work in positive numbers. I'm going to add this 1/3 in the front as well. Almost forgot to do that. And then I'm going to change this to being u to the 1/2 because it's a little bit easier to take the integral of it, or the antiderivative. Okay, so now we just have to do the antiderivative of it. Well, we just, again, similar to literally exactly what we did last time, add 1 to 1/2. Okay, we get 3/2, so u 3/2, and then multiply by the reciprocal of that. is 2/3. Solve it for 1 equals u equals u. This is u. This is u. 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 Cool. Yeah, and then you basically just plug everything in. So sort of like write this out a little bit better. 1/3, 2/3. I'm gonna write this as, it doesn't really matter. I'll do it as square root of u to the third, because that's how the power fractions work. So this is like, okay, if I have like a 3 in the numerator, that means I'm raising it to the power of 3. But if I have a 2 in the denominator, that means I'm taking the square root of it, or the root of like 2. So there could be like a 2 here, right? Yeah. And then solving this for 4 and 1. Cool. So 1/3. Bring the 4 down. I got 2/3 times 4 cubed. Yeah. Minus another 2/3 1 cubed. Simplify this. So 4 cubed is 64. Square root of 64 is 8. So I know I have 1/3, 2/3 times 8. Minus, well, 1 cubed is 1. Square root of 1 is 1. So minus is 2/3. 16/3 to multiply those, minus 2. We're almost there. 1/3. That'll be 14/3. Go 16 minus 2. And then you just multiply in to get 14/9. And that is the area under this curve from 0 to 1. So this function, how do I want to, like, I don't know. I'm just gonna like I expect it to look something like this. This is like 1. Oh wait, that wouldn't make any sense. Oh. But you know how square root functions are. Let me like look it up on Desmos really quickly. I don't want to like mess it up for you guys. 4 minus 3x. Oh, okay, yeah, I like totally messed up. Oh, because there's a negative sign. Okay, that makes sense. Cool. So it actually looks like this because of the negative sign, right, on the inside of the function. And so if 1 is like here, 0 is here, then this is 14/9, that area. I can show you. So basically from right here where my cursor is, 1, so like this spot right here. If that makes sense. Cool. 14/9. Who knew? We do. Cool. Yeah, that's all I really have on U-Sub. I'll probably be doing more examples with it as we like get closer to like the final, and if we have a third exam, I'm not sure. Oh, I know. Yeah, if we have one, I don't know. As well as, you know, future sort of integration stuff, just because they might be placing it in, mixing it into different integration problems that we'll be dealing with in the future. So yeah, that is all I really have for us today. I'm going to end it a little early because no one's here as well. So thank you so much for your time, and I hope you all have a good one.